Hey everyone, hope you all had a nice weekend. This is the next lesson. We're going to talk about direct inverse variation today. Your aim is how do we model functions via direct and inverse variation. So today's lesson is an intersection between math and science. We're going to be using a lot of formulas you might have seen in chem class or maybe physics class. So with that being said, let me get to the do now. Homework, by the way, is going to be in a handout, and I'll post that on Google Classroom as always. Okay. All right, let me jump to the slide for the do now. All right, here we are. So a bowling ball of mass 5 kilograms is propelled by a force of 10 newtons. How quickly is the bowling ball accelerating? We're going to use Newton's second law, F equals ma, which you may have seen in physics class, but if not, you will see it soon. Part B is the same bowling ball is propelled by a force of 20 newtons. What is the acceleration now? And part C is, are force and acceleration directly related or inversely related, which will bring us into our definitions for today. Okay, so pause the video now to try it on your own, but I'm going to jump to the solution now. Okay, so F equals ma, we're just going to plug and chug. So 10 newtons, that's an indication of force, right? So force of 10 newtons, we're going to plug that on the left-hand side, and then that equals 5 kilograms times a. And then if we divide both sides here, so 10 equals 5a, right? And then just divide both sides by 5, we're going to get 2 equals a. So the acceleration here is going to be 2 meters per second squared. Okay, part B. The same bowling ball is propelled by a force of 20 newtons. What is the acceleration now? Okay, so instead of 10, it's going to be 20, right? So 20 equals 5a. And then divide both sides by 5, you're going to get 4 meters per second squared. Okay, so as we can see, when the force doubles, right, from 10 to 20, the acceleration also doubles from 2 meters per second squared to 4 meters per second squared. And to answer part C, are force and acceleration directly related or inversely related? We can answer that force and acceleration are directly related. So as force increases, acceleration increases as well. Okay. And here I just note that F equals ma is an example of an equation that models direct variation. In addition to inverse variation, this is what we'll talk about today. Okay. Normally in class I would distribute worksheets, but since we're not in person, let me get to the definition. So just two definitions today. One is direct variation, the other is indirect variation. Okay. All right, I'm going to jump to the slides. All right. So direct variation. If the quantities x and y are related by an equation y equals kx for some constant k not equal to 0, because if it was 0, right, it would just be y equals 0, which is not very interesting. We say that y varies directly as x, or y is directly proportional to x, or simply y is proportional to x. The constant k is called the constant of proportionality. Okay, so that's a new vocab word, nothing fancy, just yeah. So in our F equals ma formula, right? F is the dependent variable, right? And then you can see K as the mass, I guess, in this case. And then X is the acceleration, right? So force would directly vary with respect to the acceleration, right? So as force increases, acceleration also increases. You're going to see this vocab word, by the way, constant and proportionality, on the homework. So don't get too caught up in it. It's just, yeah, so you just have to write a coefficient in front of your other variable. Okay. All right, so please pause now to copy this definition, but I'm going to keep moving to the next definition of inverse variation. Okay. All right, here we go. So inverse variation, if the quantities x and y are related by the equation y equals k divided by x for some constant k not equal to 0, we say that y is inversely proportional to x, or y varies inversely as x. Okay, so we'll see an example of that in the classwork of an inverse variation formula. But yeah, this is also very common in science. So yeah, you can probably think of a bunch of formulas that are that where two variables are inversely related with one another. Okay. But yeah, if you need to pause and copy this down, please do so right now. I'm going to move on to the next part, which I believe is an example. Okay. All right. So on the worksheet, I have this question here. So during a thunderstorm, you see the lightning before you hear the thunder, because light travels much faster than sound. The distance between you and the storm varies directly as the time interval between the lightning and the thunder. Suppose that the thunder from a storm 5,400 feet away takes 5 seconds to reach you. Determine the constant of proportionality and write the equation for the variation. Part B is, what does the constant of proportionality represent? And part C is, if the time interval between the lightning and thunder is now 8 seconds, how far away is the storm? Okay, so we're going to use, right, y equals kx is the general format that we saw in the slide just now, but since we're talking about distance and time, we'll use d equals kt, right, d for distance, t equals time, and then k is the constant of proportionality. So this might seem familiar, right? So it's d equals rt basically, right? Distance equals rate times time. Except this time we're calling the constant of proportionality k. We're using that letter instead of r. Okay, but yeah, so 5,400 feet is the distance, and then that equals k times 5, right? 5 seconds for t. And then you're going to divide both sides by 5. You're going to get k equals 5,400 divided by 5. If you do the math, you're going to get 1080 feet per second, and that will be the speed. Okay, so in other words, k equals 1080, right? So we can write the equation as d equals 1080t, right? So that's part A, right? Determine the constant of proportionality and write the equation for the variation. The constant is 1080, and the equation is d equals 1080t. All right, part B. What does the constant of proportionality represent? The constant k represents the approximate speed of sound, right? Because we just calculated how long it takes for the sound of the thunder, right, to reach us, right? It traveled to 5,400 feet, and it took 5 seconds, so that will be the speed of sound in feet per second. Okay, and then part C, time interval between lightning and thunder is now 8 seconds. How far away is the storm? Okay, so when t equals 8, right, we're going to use that same formula, d equals 1080t, so d equals 1080 times 8, so therefore the distance would be 8,640 feet. Okay. All right, pretty simple. And just FYI that if you're interested, that's 1.6 miles if you convert that to miles. Okay. Next, we are going to go to our inverse variation problem. So this one is, write an equation that expresses the statement V is inversely proportional to Z, R is proportional to I, and inversely proportional to P and T. Okay, so this is the other type of problem that you're going to see on the homework tonight. Nothing too fancy, you just write the formula, right? So just part A is V equals K over Z, right? The general formula that we saw on the slide is Y equals K over X, right? So just replacing the letters, right? We'll have V equals K over Z. And then for part B, right, we're going to have R equals K, right? We're going to have that constant of proportionality, right? K, and then it's proportional to I. So that's just another way of saying it's directly proportional to I. So we will write that in the numerator, right? K times I. You can also see this, by the way, as, right, Ki over T, right? But yeah, so scientists like to write the formula like this. So you'll probably see something like this or a format like that in your science textbooks, right? So directly proportional to I and inversely proportional to P and T. So whenever you see inversely proportional, just write those variables in the denominator. Okay, so K times I over P times T. Okay, that's your final answer for part B. And then from there, we're just going to get into a few questions applying these, right? Okay, question 1 from the classwork, the worksheet. And as always, worksheet will be on Google Classroom. So number 1, Boyle's law states that when a sample of gas is compressed at a constant temperature, the pressure of the gas is inversely proportional to the volume of the gas. So suppose the pressure of a sample of air that occupies 0.106 meters cubed at 25 degrees Celsius is 50 kilopascals. Okay, so kPa, that's a measure of pressure. Find the constant of proportionality and write the equation that expresses the inverse proportionality. Okay, so find the constant and then write the equation. All right, simple enough. I'll get to part B later. Part A is just like, right, y equals k over x, right? So we're going to replace those letters with pressure and volume, right? So P equals k over V, since we know that from the question, right, the pressure of the gas is inversely proportional to the volume. So P equals k over V. We can write 50 for pressure, right? So we have to use some outside knowledge here. So kPa is pressure, and meters cubed, that's a measure of volume. So 50 equals k divided by 0.106. And then cross multiplying, we're going to get k equals 50 times 0.106, which will be 5.3. Okay, so your equation, therefore, is P equals 5.3 over V. Okay, that's part A. And then part B, if the sample expands to a volume of 0.3 meters cubed, find the new pressure. Okay, so we're just going to plug in 0.3 meters cubed for the volume into our formula, right? So P equals 5.3, right? Using that same formula, 5.3 over 0.3, and that's about 17.7. So the new pressure is about 17.7 kilopascals. All right. For the other questions, these are similar to our second example that we did earlier, right? So we're just going to write an equation that expresses the statement. And by the way, if you need to copy down question 1 and the solution, please pause the video here. I'll be moving on to the other questions. All right. So question 2 is J is proportional to S and inversely proportional to T. Okay. All right. You'll see that these are pretty simple, right? Just proportional means numerator, right? Inversely proportional is means that the variable goes in the denominator, right? So proportional to S means that J equals K times S over T, right? We still have that constant proportionality K, right? So J equals K S over T. Then question 3, D is proportional to the square root of X. So this is pretty simple. It's just D equals K, except now it's square root of X. So instead of X, just X, you just write square root of X. Okay, so D equals K times the square root of X for 3. Question 4, we have V is proportional to the square root of X and inversely proportional to the square root of Y. So when they say the square root of Y, that means Y squared, right? And then the square root of X is square root of X, right? X to the 1/2, in other words. So we'll have V equals K times the square root of X. And then in the denominator, we have Y squared. Okay, that's number 4. And then lastly, number 5, A is proportional to the square of X and inversely proportional to T and the cube root of Y. Okay, so this is kind of wordy here, this section here. Don't get too caught up in it though. It's just, this is just saying that A is inversely proportional to T and the cube root of Y. So T and the cube root of Y both go in the denominator of the fraction. Okay, so it'll be A equals K times X squared, right? Okay, so proportional to the square of X, right? K times X squared. And then in the denominator, it's going to be T times cube root of Y. Okay, so I had to add a space here because without that space, it kind of looks like T cubed. So just to make that extra clear, added that space in, right? So T times cube root of Y. Okay, and that'll be your final answer for for question 5. Okay. And yeah, I think that's it. If you need to copy any of these solutions, please pause the video here. And yeah, other than that, please complete the homework. Oh, so this should say the handout. I just typed up the questions on a handout to make it easier. Okay, so we'll just make sure you have that. All right, but yes, that's it for today, and I'll see you all in our synchronous Zoom session soon. All right, catch you all later. Have a nice day.